And this is something that you start to getting used to the languages. So let's suppose that the textbook likes to give you an example of, let's say there's a reaction happening this way, sweet C and D. So one A reacts with 2B. So when 1 moles of A reacts with 2 moles of B, they're consuming at a different rate. And they're producing at a different rate. So there's a rate of production and rate of consumptions are different. And the reaction rate quote unquote, and this is going to we call it also the V, is this is being consumed. The concentration will go down. So change in the concentration of A, how fast it changes, right? Delta concentration over delta T, but because this concentration is going to decrease, you want to put a negative numbers. So this one is essentially positive numbers in this sense. And so I can do, well, what about this? Well, that's the change of the B concentration, BT, but I want this one in a per mole basis. And they are using this concept called extent of reaction for psi. And so to follow that, I just have to normalize this one by 1/2. Okay? So this is about consumption. And so that you can do the same. The formation, 1/3 C T 1/1 plus EP. So it's up to you which one you keep track of. You want to keep track of this one, you keep track of that, and keep track of which one are you willing to keep track of. And the usual choice is actually you want to keep track of this, something that's a normalized mole quantity. Okay? So this is a sort of the representative on this. So that's why the idea is, if you want to look at any change in the species, we learn how to use products, positive, reactant is negative numbers with extent of reaction called psi, and the reaction rate is we call this notation. Okay? We just kind of call it in general as a J, and this is a time. And but also in many times, sometimes you see that the rate, reaction rate, as a minus dt dA if for the case of A goes to P. They write this. Okay? They write that way as well. But it's the rate itself is a positive one. Okay? So remember, is sometimes we write this one for this. This one is a negative numbers, right? Remember that. So that's the one that's decreasing it. We need a negative sign to change it. And the rate law. And we say so let's say this is an example, and then we kind of say that's a rate law constant Kr, and the rate law should be generally as a function of A and the B concentration to mean the forward reaction. If you go to the backward reaction, we can do the same thing for this. But let's just deal with the forward reaction, and then this is an example. And then sometimes you will see people write Kr A power B to the B power. now I'm going to give you an example here. So this is the language. The rate is now, let's say if I write this way. That's okay. So that I think what I know is this is a first and first. So it's a first order in A, first order in B, right? And then what do you say? Second order overall. So those are the languages that people say. Okay? So let's say you have done your experiment to measure the reaction rate, and it depends on the concentration A to linear, concentration B to the linear, and you find out this is something that there is. Okay. But now, complex. Okay? So let me write the equation. This is one of the famous equations. You guys can Google this one too. When hydrogen react with bromine gas, you want to 2HBr. Okay. Think about it. Okay, so this when hydrogen meets a bromine, you make an HBr. And then people measure the rate, and then I want to write the rate here. This one is important, and I want you to build the right concept on this, because it is actually very. I'm giving a very oversimplified version on this, but it is very complicated business, and then that's why all the chemical companies still doing a lot of research on this. Okay? For that reaction, the rate constant, I'm just writing this for as a fun, okay? So don't get scared. Br squared Kb HBr Ka H2 Br2 C over T. Like, what is this? Okay, so this is a rate reaction. Actually has been verified. Okay? They have verified this by increasing the hydrogen pressure, hydrogen concentration. They follow this relationship of when you increase the bromine pressure, they have a much more complicated pattern that they follow this. And they have figured out. And so what's going on? I mean, I thought the rate is always something like, nicely speaking, A to the power of A, B to the power of B, or something like that. This is what I thought, but this is not. And the reason is because we are only, I'm going to write this equation one more time. This reaction, I just write it here, is not net reaction. It is a net reaction. Okay? It is what we call is the element. This is called the elementary reactions. It's a combination of elementary reaction to give a rise to this. So this collision idea, this equation, for example, here, it seems to be very simple and is actually very useful. Okay? This one is not bad and actually works really well. Only if A collide with B becomes something else. Right? But this one, as an example here, what's going here is this is just a net reaction. It's not hydrogen and bromine reacts and they switch the partners. They don't do that. Okay. So what happened here is I'm going to just write it down, and people has done that. This is actually is in the internet, not in the textbook, because the textbook just want to say some cases like this, some cases more complicated. So it is not like you can predict what's the rate law. If they say what's the rate law, and then you can do all the things, or if they show the data, then you can estimate it. Sometimes it's very complicated. And the elementary reaction this one goes through is first, brome is a very soft molecule. They like to be dissociated into brome radical. I guess so that's a K1. That's an elementary reaction. So I can do that. And then the brome radical meets with a hydrogen, and then they produce HBr plus H. So that's a K2. And H radical react with Br. And this one is really a collision process, right? When they collide each other, they produce HBr, and then I guess a Br minus, Br radical is being formed, and that's a K3, blah, blah, blah. So it's like there are 5 processes combined together, and the 5 processes, and there's a K1, K2, they find the most significant steps, K5, and this combination of this become Ka value and Kb values, and they come up with this. Okay, this to solve this one, I think that it is actually a full day lecture to do, and it's not easy. But what I'm trying to say here is, you have to build up the eyes about what we call the elementary reaction or not. Okay? This is actually a very complex reaction. Okay? But when somebody say, oh, A decays into product, this is probably the most seemingly easiest reaction, that the decay process into this, and then I don't have to worry about the more complex mechanism, and that's what the integrated law is all about. Okay, so I guess what I want to say. So you don't have to remember this, just to learn the right languages. And how to determination, rate law. And how do we do that? And we'll call the method of initial concentration. Okay, so think about it. We are measuring the method in the beginning, and then we can change the concentration of A naught, concentration of B naught, and you can double the concentration of A, and the initial reaction rate double, and then that's linear. If you double this, and this one is quadruple, that means it's to the square, so you can figure that out. And if B, you double it, nothing happens, that means it's not depending on B. So you guys can figure that out, and figure the rate law. Oh. So that's to the A, to the B, and you can figure that out. Because the real rate law is about K at A and B. What that means is, at any time, they are looking at any time, this concentration is a function of time, and so that's a rate, and this is keep on changing. But you want to do what is called the initial concentration to essentially easily measure as soon as you mix those, and within a few seconds, or less than a minute or something like that, and you want to measure this, and then you change the condition and keep on measuring that. So therefore you can make a measurement of the rate law, power, and the rate constant as they are. And so that's what I'm looking to. I think it's a good point for me to have a check on this. What is a unit on this? I mean, it's the same unit. What's the rate? No? Remember? This is concentration change over delta T, right? Remember that? It's like, so therefore, it is mole per liter, if you want. If you use a pressure, there will be pressure. Okay. Mole per liter. Okay. So that's a unit. And this is the unit that you see is a mole per liter. This is a unit of mole per liter. If it is a overall second order reaction, the K value should have a unit of liter per mole, 1/2. So that you can have I should say second. So 1/2, 1/2, and this one is essentially make sure that mole per liter concentration only so high. So this rate constant has a complex unit depending on the power law. Okay.